So, welcome to the special interest group meeting. Scott's wandering around in the far reaches of the Sierras, apparently unable to connect to cellular, or either that or unwilling to connect to cellular, so that he can host this thing. Before we get started with Bill's presentation here, just real quick, just kind of talk a little bit about what's going on next month. So next month, Scott has asked me to put together how I process tarot image data. So we did this last year and it turned out pretty good. So in July, we're going to go ahead and give everybody a choice. Give everybody a choice of 3 different data sets that have been collected by tarot over the past couple of years. And what I'll do is I'll post a link in the chat window here shortly. So this is a folder specifically for the AISIG group, and it contains 3 complete data sets. I should say 2 data sets plus a bunch of masters. So the data sets that you guys will get to select from, there's 36 hours of imaging data, LRGB, HA, S2, and O2, and O3, plus flats, biases, and darks for the Christmas tree cluster. This is the same. This is the same image data set that Stuart Foreman a few months ago had used to create his how do I do it? How do I process this stuff? This is an incredible good amount of data. Everything in it, the signal to noise ratio after we got done with this stuff, as far as collecting it, was tremendously good. So that's the file. If you've not seen it in the past, let me show you something here real quick. So that's just the HA data for this stuff. And the HA data is just absolutely remarkable. That's about 12 hours of HA data out of the 36 that are in there. So we put a lot of time into HA. There's the O3 data looks pretty phenomenal, as does the S2 stuff. And I know that Stuart had only used when he did his stuff, he basically used the LRGB plus the HA and mixed that with the luminance channel. So this stuff's in there, so you can go play around with that and see what you come up. That'll be pretty good. That'll be part of the data set. Back to here. M63. This is a really, really clean set of our LRGB flat, and a couple of other members have used this data to produce an extraordinary set of images off this data. There's 20 hours of LRGB data in here. So again, this is a full data set, and just be aware that the Christmas tree cluster and the M63 data sets they're almost 5 gigabytes worth of data. So if you're going to go download this stuff, just remember it's going to take a while to get it down, depending on your internet speed. But it's all in there, so you can start over from soup to nuts, ground zero. If you're a PixInsight fanatic, the weighted batch pre-processing version 2 has just been released out there, and it has some remarkable capabilities in it if you're so inclined to follow along with what's going on with PixInsight. Last but not least is the Wizard data collection, and so this is there's actually the Wizard. There's 40 hours of imaging time in the Wizard, and this isn't a full data set. So this is the submasters. So this is basically you're getting the submasters. And in this particular instance, I've included both the XISF, if you're a PixInsight fan, and I've included also the FITS format files if you want to use something else to process them. So FITS and XSIF are both in there. And again, they produced some really remarkably good data. Just to give you kind of a quick show and tell. So depending on how you want to do it, there's just the LRGB stuff. You can go in and play around with the HA. if you want to blend HA and LRGB, there's just tons and tons of data in there. You can go play around with combinations of HA. This is an HA03 combination, and there is what you get when you use the Hubble palette. So just a huge amount of data to play with. And again, this is done both FITS and XISF, depending on what software stuff you want to play with. If you can, like I said, I'll in a few minutes here, I'll post up the link in the chat window, and you can copy that link, and that'll take you right to the Google Drive. I'll also post that stuff up on the XIO forum or the IO forums, and people can grab it from there. If you guys got any problems getting to the data, just send me a note, taro@sdaa.org or president@sdaa.org, and we'll figure out how to get you the data. But there's some tremendous stuff in there. And again, the idea here is to take the data, go play with it, and then step through. Go ahead and step through with the group what you did to process the data. So, without further ado, Bill Jacobs, you ready to start chatting?
I sure am.
Okay.
Okay, I'll see if I can share my screen. Looks like you need to unshare your screen.
I do. I will stop it right now. All right, all yours there, Captain.
Okay, share. See if that works. Okay, you should see the notes page and the next slide page. And if I swap them here, you should just get the full screen of my presentation. And I need to make this disappear over here. Voila. Can you see this little annoying talking thing? Oh, I can make that disappear too. Okay, we are ready to go. So this is a presentation that I put together at the request of a friend of mine that teaches community college astronomy and physics at La Positas Community College up in Livermore, California. And I gave this talk during his previous semester, and it was pretty well received, so I was happy about that. And I'm going to be planning on giving this talk to future semesters when he gives the astronomy course up there. And I sent it on to the outreach folks in San Diego Astronomy Association, thinking maybe they could connect me up with other astronomy classes that might be interested. And Scott Dixon took a look at it, and he thought it would be a really good presentation for the Astroimaging SIG group, and that's why I'm here. So this is my presentation, Amateur Astrophotography, my experience. It's not meant to be a tutorial on astrophotography, but rather something aimed at a community college class to maybe get them interested in astrophotography, teach them about what's entailed in doing it, and then also include a bit of science and technology history and a bit of astronomy, astrophysics, and cosmology that's related to the various objects that I'm going to show. So hopefully they learn something. So with all that in mind, if you have any, in watching this presentation, if you have any ideas for me that might improve this as an outreach presentation, that would be appreciated. And certainly I hope that you guys enjoy the presentation as well. So this is an outline. The first section will be raw image data acquisition. Can you guys see the arrow as I show it on the screen? Is the arrow visible? Yeah. Okay,
yeah, that's good.
Okay. So the first section is raw image data acquisition, the hardware equipment I use, the software, what's entailed with an imaging session when you go out to image the sky. The next section will be just one chart on the image processing process, which is very important, and it gets you from the raw image data to your final image. And then I will sort of go through a tour of the night sky with focusing on a whole set of different types of objects, and the list of them is here. Raw image data acquisition, the hardware equipment you need. Well, it turns out most people think that when folks are looking through a telescope, they're looking at little tiny objects that are very small, but in fact, quite often it's not that you're looking at a very small object, but that you're trying to image a very faint object. And thus you need a long time exposure to image it, and you sort of have a problem in that we know that the Earth is rotating from west to east, making it look like objects that are on the fixed celestial sphere are moving across the sky from east to west. So this is a problem when you're doing long time exposures. So you need your equipment, your telescope mount, to compensate for the Earth's rotation, to remain pointed at an object, your target object that's on the fixed celestial sphere. So the way you do this is very simple. Is this are these the mute and the stop video? Is that showing up on your screen? Because that was not there before. Is it blocking part of the image or not? Well, hopefully it's not. So this is a picture of my setup, and the idea is that you have a mount that you align such that the right ascension axis, and I guess I should have pointed out that right ascension is the direction along the rotation of around the Earth's axis, and declination is the coordinate that's normal to right ascension. So you want to set up your equatorially aligned telescope mount such that its right ascension axis aligns with Earth's polar axis, and such that it will then rotate from east to west to exactly compensate for the Earth's rotation from west to east, to keep your telescope pointed at a fixed object in the celestial sky. And therefore then you can take a long time exposure. And I want to point out here that in my setup, it seems kind of peculiar, but my camera here is pointed out the front of the telescope, and I will explain that a little bit more on the next slide. So on the left, I have a picture of the sort of the complete setup. It includes the mount right here, which I just talked about, and then the heart of the whole system, which is the telescope, the main telescope tube itself. It's a Schmidt-Cassegrain telescope. And on the previous slide, I showed the camera sticking out the front, and it's hidden behind this extension to the telescope tube called a dew shield, but the camera is right in here. So a Schmidt-Cassegrain telescope is a reflecting telescope. It has a spherical mirror. The light comes in, reflects off the primary mirror. In the standard setup, there's a secondary mirror. The light reflects that back to where you'd either be looking through the eyepiece with your eye, or if you wanted, you could mount a camera here. In this standard setup, the telescope would be a 2,000 millimeter focal length at f10. If you're a photographer, you're familiar with this nomenclature. It's the same for telescopes as it is for normal cameras. Now, in my setup, which is a very common setup to use with this type of telescope, the secondary mirror is replaced with a primary focusing lens. The primary focusing lens then focuses the light off the primary mirror at the primary focus on your camera focal plane sensor. This camera is very similar to a camera that you might own, with two main differences. One is that commercial cameras all have a filter on the front that filters out not only IR light, but part of the red spectrum. And on a camera that is customized for astrophotography, that filter is removed. And typically you place, well, in my system, a filter is placed there that filters out the IR, but lets all the red light through. The only other real main difference in the camera functionally is that it has a thermoelectric cooler on the back of the focal plane that cools the focal plane sensor to reduce the amount of noise that you get when you're taking long time exposures. And in this setup, the focal length is reduced to 400 millimeters at f2. So if you're familiar with cameras, the idea here is that you have a very fast telescope for shortening what otherwise would be really, really long time exposures. So a diagram of the setup that you see in the picture on the left is shown right here, and it gives a kind of a full description of the way the system works. There's a mount controller that allows you to tell the mount to rotate around the polar Earth access. And it also serves to do some other functions to allow you to easily slew to objects in the sky. The imaging camera sends its imaging data to the computer. The computer communicates the other direction to send control commands to the imaging camera. There's actually a second telescope and camera in the system that's used to correct for the tracking. The camera, the telescope mount itself isn't perfect, and you want to actively correct. So the way that works is that the computer sends control commands to the tracking camera sends its image data to the computer, and then the computer analyzes that data and sends corrections to the mount to keep pointed at an object in the sky. And it sounds a little bit complicated, but this picture helps explain it. This is actually the software used to do this. And you can see in this image, which is coming from that tracking camera, it updates every second or so. You can see that there's a bunch of little dots here, which are stars, and there's actually a star right here at the crosshair. And the software basically monitors the position of this star that's at the crosshairs. And if it starts to drift away from the crosshairs, it sends a command to the mount to nudge the mount in the proper direction to keep this star right at the crosshairs. And you can see up in the top is a graph that gives the error in the tracking, and each one of these spikes is when the software sent a command to the mount to nudge the mount in one direction or the other to keep it pointed exactly at this star. So I do have here a quick description of the details of my system if you're interested. It's a Celestron 8-inch Schmidt-Cassegrain. My camera is a QHY10. It's 10 megapixel CCD, one-shot color and cooled. The field of view of the system is a little bit more than 3 degrees. Note that the moon subtends about 32 arc minutes. So this is between 6 and 7 moon diameters. So that might be bigger than what you might think, but there's many interesting objects to view out in the night sky that are a good fit for that field of view. The resolution of my system, based on the pixel pitch, is about 3 arc seconds per pixel. And then the tracking scope is the Orion Starshoot camera and guide scope. I use the PhD software, and for data for the image camera acquisition, I use Nebulosity. So where did all this stuff come from? It just didn't pop up into thin air. There's been a long history of technology development that has led to a rather lazy amateur like me to be able to take reasonably good images. And I sort of have a list of the key technology developments that I see were the most important ones to get to such a system. So starting in the 1300s, glass lenses were developed for the use for spectacles. It wasn't until 1608 that the first working refracting telescope was developed by Hans Lippershey. Back then, things are very much like they are today, and that the very, very first telescope that he built was delivered to the Prince Maurice of Nassau for military application. But shortly thereafter, the scientists got a hold of it. Galileo soon utilized and refined the design for astronomy. So about 25 years later, the reflecting telescope designs started to mature. And you can see between 1636 and culminating in 1672, when Laurent Cassegrain developed the Cassegrain reflecting telescope. And you can see that my Schmidt-Cassegrain telescope is a descendant of this Cassegrain reflecting telescope dating to 1672. The next important developments that in my view, 1733 is achromatic lenses developed by Chester Moore Hall. And basically what this is developing lenses that will focus at different wavelengths or different colors of light all at the same place on the focal plane. And this is particularly important for wideband imaging like my one-shot color cam. So you get all the different colors to focus properly. So all of the things up until this time have been dealing just with the telescope itself. For astrophotography, in 1871, the dry plate photographic process was developed by Richard Leach Maddox. And very shortly thereafter, astrophotographers started to image things with their telescopes. In 1932, aluminized coatings on the ground glass mirrors were developed by John Donovan Strong. And this was a very important development for amateur astrophotographers, in that before this time they used silver coatings, which would oxidize and tarnish. And it would be a major ordeal to keep your telescope collecting light efficiently. So even with the dry plate process, folks in between 1871 and up until the turn of the 21st century had to use the regular photographic process to do astrophotography, and that is truly a labor of love, certainly based on what we're used to today. And in 1969, the first charge coupled device CCD optical sensor was developed at Fairchild Semiconductors. The chip that they had as of 1974 was a 100 by 100 or 10 kilopixel CCD, which Kodak used in 1975 in the first digital camera using this chip. Now you can see that in my system, I have a 10 million pixel camera. In 1974, they had a 10,000 pixel camera. So it took well into the 21st century until this CCD and later CMOS optical sensor chips reached the stage where you could take images like the ones that I'm going to show you. Now, even with all that, you would still really be nowhere unless you had both control and processing power that's available with personal computers. The personal computer was sort of developed circa between 1973 and 1981. It was enabled by advances in semiconductor technology dating to the late 1950s. So I can say that on a personal note, I was in college up until 1981, and I was interested in astrophotography and dabbled in what you could do back then. And in the years past 1981, when computers also advanced, much like the CCD sensors, to enable systems that are inexpensive, that you can take images like I'm going to show, that was really just a dream. So for amateur astrophotography, we are kind of in a golden age that someone my age would have not accurately predicted when we were in college. Okay, so that sort of covers the basic equipment for an imaging session. When you go out to look at the stars and say, I want to get an image of that, you have all this equipment, and it's not just go hit the button, take the picture, and go home. There's quite a few steps that you need to go through to get your image, and I sort of go through the steps on this chart. First, you need to align your tracking telescope with your imaging telescope. You need to position your mount so that it's pointed approximately north, and you need to level the mount. Then you need to adjust the mount altitude based on the latitude of the site you're at. And when Polaris becomes visible, you need to point your telescope to 90-degree declination, perform a rough focus, and then adjust the mount azimuth and altitude to center Polaris. Now, even doing all of that manual alignment, it's not nearly good enough to actually image. You need to have your polar alignment more accurate than that. There's several different techniques to do it. I use the plate solving method using SharpCap software. And it's particularly easy in my setup because my imaging camera has a relatively wide field of view, a 3-degree field of view, which is well matched to the plate solving algorithms that are out there. What the plate solving does is it basically, you take a picture of the night sky right around the North Pole, and then you rotate your mount by say 90 degrees, and it watches where those stars move, and it figures out where your right ascension, your mount right ascension axis is. And you can see that's marked here by a red X. The software also knows, based on the stars, that it's identified where polar north is, and that's the green X. Okay, and you can see that they should be perfectly aligned, but they're not. So the software then identifies one particular star and instructs you to adjust the altitude and azimuth of your mount to move that star into the center of a circle, and then you are polar aligned. So that's sort of a summary of how that works, and it's really quite simple. So then the next steps before you can finally take an image is you point your telescope at the meridian on the celestial equator, and you perform a very easy calibration of your tracking software so that your tracking algorithm knows how far the telescope moves when it tells it to nudge. Then you perform a telescope mount go-to alignment procedure using the mount controller. This is basically a procedure that's automated through the mount controller so that the telescope can figure out exactly where it's pointed, so that you can then punch into the mount controller any target object you want to go to by name or by its documented right ascension and declination, and the telescope will automatically slew to the object that you want to view. You can then do some fine framing to get your image just the way you want to. You perform a fine focus procedure. There's software out here to aid you in doing that, and I use the fine focus procedure that's integrated with the nebulosity software. And finally, you're ready to begin taking your image at that point. So you've done all that, and you take your first image for, say, 180-second exposure. You had looked up that imaging the Flame Nebula and the Horsehead Nebula is a very beautiful image, so you thought that would be your first one. And you bring up the image that you just took after your 180-second exposure, and it looks like this, and you can't see any nebula at all. But never fear, you just have to do some digital processing. So the first steps of the processing procedure are linear processing steps, because they involve linear mathematical operations. And that first step is that it turns out that in this image, I'm displaying the image based on the full scale of my optical sensor, which is a 16-bit sensor. So the pixels saturate when the each individual pixel has done 2 to the 16 counts, I guess we'll call them, or the pixel values is 2 to the 16. But if we just tell the computer to render that image such that instead of making 2 to the 16 white, we're going to make 1500 white, then you can see that there's a lot of data in the image. It is just too faint for us to see. It's just in the bottom bunch of bits of the optical sensor. So the second step of the processing is to subtract out the counts that are due to dark current, and then divide by a flat. The dark current, essentially the dark frame, is if you put a cap on your camera and you do an exposure for the same length of time, the same 180-second, well, it turns out that just due to the electronics, that all the pixels register some value, and you want to subtract out that dark value. And then dividing by a flat, this is the same with any camera system. I think you're familiar with the with vignetting that you get if you're a photographer and using a wide angle lens. You get some vignetting in the corner of your image where the corners are darker, and you want to divide that as well. So you can see that after that step, we're starting to get to an image that looks a little bit better. The next step is for a one-shot color camera is called debayering. On a full color camera, half the pixels are behind a green filter, a quarter of the pixels are behind a red filter, and a quarter of the pixels are behind a blue filter, and you want to render the image assigning the correct color to each pixel. So you do that, and you now have converted from a black and white image into a color image. And then the last processing step is that you actually don't just take one image, you take a whole set of images and you average them together. And the reason for doing this is to improve your signal to noise ratio. And if I expand this, I think that you can see with the single exposure, this image is quite grainy. And after taking 40 180-second exposures and averaging them together, you've improved the signal to noise ratio and gotten rid of a lot of the noise that you see in the single. So that's the end of the linear processing. You then proceed to a nonlinear processing steps. The first step is where you do a nonlinear pixel stretch, basically using a nonlinear function to reassign intensity values to the pixel. And I give an example of such a function. Some people might think that this is in some way cheating in doing your processing and not what you really see, but that really in some sense is not the case, because for instance, the response to your eye isn't linear. And in fact, just with a normal camera, when you're taking images, your camera does a similar, though less dramatic, nonlinear stretch on all the images that it takes. So finally, and I point out that I do all these steps using Nebulosity software. And then in the final processing steps, I use raw therapy, which is just a general purpose photography package, not specific to astrophotography, to fine tune the exposure, black level, contrast. For astrophotography, local contrast is very important to enhance your images. Color balance, color saturation, and then also different than most standard types of photography is that since the things you're imaging don't move, you can come back on a different night, maybe with a different setup, and take more data and then combine that. And in this final image, I've combined it with some data that I took on another night that had a filter that effectively enhances the H-alpha red emission to improve the image, and voila, you get from this image up in the left to kind of a rather beautiful looking image that you see here. So typically I take nominally 180-second exposures, sometimes 240, sometimes 120, depending on what it is. And I think I've gone through the basic processing. I'll point out that I do some other processing, labeling, coma correction, and image stitching that I've implemented myself in Python. And if you're interested in the labeling, coma correction code, remind me at the end of the talk, and I have a couple of charts that I can show on that Python code. Okay, so alas, we're to our tour of the night sky, but not quite, because I'm always disappointed to learn that the vast majority of people have very, very little understanding of how far away things are. And for me, when you're doing astrophotography, it's integral to really understand what you're imaging, to understand where things are and how far they are. So I have a little chart here on astronomical distances. 1 light year is the distance that light travels in a year. 1 astronomical unit is the distance from the Earth to the sun. Okay, so 1 light year, turns out it's approximately equal to 60,000 astronomical units, and it's approximately equal to 10 trillion kilometers. Okay, so it's a very large distance. So what are the distances to various things? And this is sort of what I wanted to get at, so that you can have some appreciation for the objects that you're looking at through your telescope. The distance from the Earth to the sun is 500 light seconds. The distance to the next nearest star is about 4.3 light years. The diameter of our galaxy, the Milky Way, is 200,000 light years. About 10 times larger than that is the distance to the nearest galaxy, about 2 million light years, and about 2,000 times larger than that is the radius of the observable universe, 46 billion light years. Okay, so the objects that we're going to look at and keep in mind, these distances within our solar system, the comet, which is less than 1 light year away. Within the Milky Way galaxy, we're going to look at a star which is just 6 light years away. Open clusters, the Pleiades we'll look at, which is 440 light years away. Nebula that are various different distances, up to 5,700 light years away. A globular cluster, which is a good fraction of the way across the Milky Way. And then beyond our galaxy, we'll look at galaxies, a galaxy cluster, and a quasar, which is about a 20th the radius of the universe, the observable universe away. So with that, I'm not going to show the objects based on how far away they are, but based upon what time of year you go out to view. So it's a February night. You could have looked up and seen the Flame and Horsehead Nebula, which I just showed. I'm going to show 2 more objects, the Pleiades and Orion. So this is my first image of the star cluster, open cluster, the Pleiades, and I show here the moon that is superimposed, just to give you an idea of what the field of view is of this image. So what's an open cluster? Okay, an open cluster is a group of up to a few thousand stars of roughly the same age that are formed from the gravitational collapse of a giant molecular cloud. So for instance, within a nebula. The stars are closely bound by mutual gravitational attraction. And in fact, they lose members over time as a result of close encounters with each other and get flung out. I think that you're probably familiar if you keep track of the space probes that NASA sends out, that they use this technique where a space probe might go by a large planet like Jupiter, and as it approaches Jupiter, it gains speed, and that gain of speed sort of acts like a slingshot effect, where it gets slingshot past Jupiter. It picks up enough speed that it's able to get flung out of the gravitational field of Jupiter and head on out into the outer solar system. Well, the same thing happens with stars in an open cluster. They appear fixed, but actually over a long enough period of time, they move around. And every once in a while, they have a close encounter with another star and get flung out of the open cluster. So therefore, these open clusters do not survive forever, and they have typical lifetimes of a few 100 million years. So the Pleiades is prominent to the naked eye in the winter sky. Probably most of you have looked up and seen it. And as such, it's been recognized since antiquity to cultures around the world. Therefore, depending on where you live, you might know it by different names. In English-speaking countries, it's known as the Seven Sisters. In Japan, it's known as Subaru. This is an image of the Nebra sky disk, which was discovered in Germany in 1999. It was dated to the Bronze Age, I believe this is, 1600 BC. And this group of dots here on the Nebra sky disk is believed to be the Pleiades. And of course, that's just conjecture. You can't go back and ask anyone, but it looks like the Pleiades to me. In popular culture, we see the Pleiades as well. This is the back of my Subaru Outback, and you can see the emblem, the Subaru emblem on my car. So Galileo was the first person to view the Pleiades through a telescope and discovered that it contained many stars that were too dim to be seen with the naked eye. He published his observations in his famous treatise, The Starry Night, and it shows 36 stars. This was published in 1610. Now, of course, he didn't have photography, so instead looked through the telescope and made a sketch. So in some sense, this is a very, very early astrophotography. I guess I should also point out that in the star cluster, you can see two nebula associated with two of the brighter stars that are illuminated by two of the brighter stars in the cluster, and that's this wispiness that you see. This wispiness only appears if you take a long time exposure. You can see that in this image, I took 30 exposures, each 240 seconds for 120-minute exposure. And on the next chart, I will talk more about nebula. Okay, so this is the Orion Nebula. The Orion Nebula is located in Orion's sword. It is visible with the naked eye and was first observed in a telescope in 1610. Remember, the telescope was developed in 1608. So just like Galileo pointed it at an open cluster about the same year, it was pointed at the Orion Nebula, and thus the Orion Nebula was the first nebula discovered. At the time, they didn't know they didn't call it a nebula. They didn't know what a nebula was. They just knew it was this fuzzy thing up there. So what is a nebula? I guess is the next good question. There are three basic types of nebulas: H2 regions, supernova remnants, and planetary nebula. The Orion Nebula is an H2 region, which is a large diffuse gaseous region, much less dense than air. It's composed, the H2 regions are composed of approximately 90% hydrogen, 10% helium, and trace amounts of other heavier elements. There are three basic types of H2 region nebula: emission nebula, reflection nebula, and dark nebula. In an emission nebula, the observed light is from the spectral line radiation of atoms in the H2 region, which have been excited by energetic incident starlight. In a reflection nebula, the observed light is from scattered light is from scattered incident starlight. So you have bright stars that are shining light. It gets scattered off this cloud and directed towards us where we can view it. So what causes the colors that you see in the nebula? Emission nebula are often dominated by the red H alpha emission. You also get some blue-green color from the H hydrogen beta and blue hydrogen gamma line, and green color from oxygen 3 lines. In reflection nebula, and the Running Man Nebula here is a reflection nebula. They are red and orange when they're dominated by light from illumination behind the object. This is due to absorption and scattering effects, which is similar to the same effects that make sunsets look orange and red. And reflection nebula are blue when they're dominated by reflected light. This is due to Rayleigh scattering, and it's the same reason that the sky is blue. So this is one of the images that shows considerable detail. So I'll just zoom in on it a bit, and you can get a better idea of what's possible with an imaging system of the quality that I use. Okay, I will show later in the presentation a supernova remnant, the Veil Nebula. And I do not have any images of planetary nebula. Just wanted to point out that planetary nebula have nothing to do with planets. They're the remnants of celestial objects called white dwarf stars. So I mentioned that before that you can get star forming regions in large molecular clouds, and the star forming region in Orion has been studied extensively because it's the closest star forming region to us. What's amazing to me is that the brightest stars in the Orion Nebula are as young as 10,000 years old. So these are you think of the age of the sun and the earth in billions of years, and the age of some of the stars in the heart of the Orion Nebula are just 10,000 years old. So as the Orion Nebula is the brightest nebula, it was also the first one photographed in 1880, which was just, I think, 9 years after the dry plate process was developed. Photographer Henry Draper, with a 23-centimeter refractor and using the dry plate process, took this image of the Orion Nebula. You can see these three stars right here are the three stars right there. And these two stars right here are these two stars right here. Just 3 years later, Andrew Common, using a 91-centimeter reflector and a dry plate process, took this image where you can really start to see the full Orion Nebula, including Damaran's Nebula right here. And you can see the same three stars right here, which are those three, along with several other stars that you can identify that map directly on. So as one might guess, the Orion Nebula hasn't changed a whole lot in 100 and some odd years. So, okay, so you go out to image some 3 months later in May, and the night sky has moved around a bit. And in this area of the sky, we're going to look at 4 different objects: Bode's Galaxy, M106 Galaxy, the Virgo Galaxy Cluster, and a quasar. So Bode's Galaxy is the large one here. The Cigar Galaxy is right here. I'll quickly zoom in so you can get just a little bit better look at what these things look like with my imaging system. So what is a galaxy? Galaxy is a gravitationally bound system of ordinary matter, stars, they're planetary systems, stellar remnants, dust, interstellar gas, and dark matter. And we will talk a little bit more about dark matter related to some of the other objects that we look at. Galaxies range in size from dwarf galaxies with a few 100 million stars to galaxies of 100 trillion stars. The ordinary matter in a galaxy is typically distributed in elliptical or spiral disks, like the ones you see here. The more abundant dark matter has a larger spherical geometry, which is called the dark matter halo. So Bode's Galaxy has an interesting distinction. It is the most distant large blue shifted galaxy. And blue shifted means that it is moving towards us, not away from us. I think that you understand that or have been taught that the universe is expanding. So in general, all objects in the universe are moving away from each other, but things that are in the same gravitational system are gravitationally attracted to each other. So if that gravitational attraction is strong enough, then they will be moving towards each other. And it's interesting, at least I think it's interesting to note that based on our current understanding of cosmology, in about 1 trillion years from now, Bode's Galaxy and all the other blue shifted galaxies will have merged with the Milky Way, while the entire rest of the currently observed universe will have receded from view, in principle, due to the expansion of the universe, i.e., everything else will no longer be part of the observable universe. We'll be all alone with just the stuff that was in our gravitational well. Now, I wouldn't get too upset about this because A, you're not going to be around, and B, maybe in the next 20, 30, or 40 years, our current understanding of cosmology will have changed, and we'll have a new understanding of how the universe is going to evolve. So the next image I have is of a galaxy cluster. This is the Virgo cluster. The average distance to the galaxies in the Virgo galaxy cluster are 54 million light years. So what is this notion of a galaxy cluster? I mean, who would have thought that the galaxy even would be clustered? So I'll try and explain that in this chart. This chart shows what is known as the local group of galaxies, which our own galaxy, the Milky Way galaxy, is in. You can see here is the Milky Way galaxy. The next nearest galaxy to us, which is just a couple million, 2 million light years away, is the Andromeda galaxy. I'm going to show you an image of that later. Now, the local group is embedded along with the Virgo cluster inside a larger supercluster called the Laniakea supercluster. So this local cluster, which is about 5 million light years in diameter, is embedded here in the Laniakea cluster, which is about 500 million light years in diameter. So I don't have this quite to scale. This little circle is about twice as big as it should be for the local group. You can see here is the M81 group. That's where Bode's galaxy is. And then some distance further away is this Virgo galaxy cluster. Okay. Now, I should also note that this 500 million light year, recall I had mentioned that the observable universe is 46 billion light years in radius. So this represents about 1% of the diameter of the universe. And on this scale, on the 500 million light year scale, the universe is relatively uniform, and you don't then have things that look like these filaments or clusters. But on smaller scales like this, you do. So this kind of gives a good feel for the whole scale of the universe, going from the observable universe down to 1% of the diameter in this supercluster that we see, down to our local group, down to our galaxy, and then our solar system within the galaxy. So you can see that there, immediately you can see quite a few galaxies in this cluster. If you were to count them at first glance, you'd see maybe 40 some odd galaxies. But in fact, if using the labeling procedure routine that I wrote, I've now labeled all galaxies that are brighter than magnitude 18 within 1 degree of the image center. And I forget how many are on this. I think it's about 90 galaxies that it shows. And in fact, if I look up, I'm not cheating. Inside each one of these tick marks, you can see there's something that's kind of fuzzy that doesn't really quite look like a star. And in fact, they're all galaxies. And I'll point out a couple in particular. This brightest one is Messier 87, which I'll talk about in a little bit more detail. But this guy right here is kind of an interesting one. It's a little bit of a surprise, VPC 0791. It turns out that it's not a member of the Virgo galaxy cluster at all. It just happens to be in the same direction. VPC 079 is actually, 0791 is actually 1.24 billion light years away. So it's about 2.5% of the way across the observable universe. And its absolute magnitude is as bright as M87, but it's just a long way away. So it's kind of interesting when you look in more detail at your images, you can find things there that you weren't expecting. So I mentioned that M87, it is the most well-known member of the Virgo cluster, and it contains a supermassive black hole at its center, and it was famously imaged just recently by the Event Horizon Telescope in April 2019. And this is the image that was taken by the Event Horizon Telescope. Just to give you an idea of the resolution of this image, it was taken with synthetic aperture imaging, millimeter wave at 1.3 millimeter. So what you're looking at here is in false color. It's really a millimeter wave image that's rendered in an optical wavelength so that you can see it. The diffraction limited resolution of the Event Horizon Telescope is 25 micro arc seconds, which is mind-boggling to folks that do amateur optical astronomy. Recall that my system has a resolution of 3 arc seconds. So this has a resolution that's about 100,000 times better than the resolution of my optical system. And for you data processors, it's very interesting that I show here what 50 micro arc seconds is on this image. So the whole diameter of the event horizon of the super black hole is just a little bit more than 50 micro arc seconds, yet the diffraction limited resolution of the system is 25 micro arc seconds. So they show resolution well beyond the diffraction limited resolution. And if you read their papers to understand this, they do a whole lot of processing to be able to arrive at an image like that with enough confidence to know that it is real data. And I think that's all I have on the Virgo galaxy cluster. So our next object is a rather exotic object known as a quasar. It's 3C273. It was the first quasar that was identified. If we look at it in my image, it's just like a dot, looks no different than a star, but it's no ordinary thing. It's not a star. So what is a quasar? In the earliest radio surveys of the sky done in the 1950s, some radio sources coincided with objects that appeared to be unusually blue stars. Because of their almost star-like appearance, they were dubbed quasi-stellar radio sources, later shortened to quasar. So this object is 2.4 billion light years away, about 5% of the way across the observable universe. It's about 4 trillion times the luminosity of the sun at visible wavelengths, and has a very large black hole in its center with a mass of approximately 1 billion solar masses. So the optical spectra of 3C273 was measured by Martin Schmidt at Palomar Observatory in 1963. I might point out that maybe Scott Dixon on his way to the Sierra drove up 395 near Bishop. And if you look out to the east, you can see the Caltech radio observatory out there. And back in the 60s, they used that radio observatory to identify quasars, and then used the survey from the survey telescopes on Palomar to match them up with optical sources. Martin Schmidt then used the 200-inch telescope on Palomar, perched up at the primary focus with his spectrometer for hours on end to take the spectra, and took the spectra of C3273. But when he took the data, went back and looked at it, it was very confusing and he didn't understand it. And after 6 weeks, he recognized that the emission lines were from hydrogen atoms that had been redshifted with a redshift of 1.58, which was a much larger redshift than any previously observed object. Based on this redshift, it followed that 3C273 was the most distant luminous object yet identified in the universe. And Martin apparently this was a pretty disconcerting discovery for him, and made him really scratch his head. And the story goes that when he returned home that night, the first thing he said to his wife was, "Something terrible happened at the office." And I guess I can sort of understand that, like back in my days when I was working, when something happened I couldn't explain that was going to be of interest to folks, it caused a lot of self-doubt. And it's just interesting to me that he didn't feel so great the day he figured this out. So further studies revealed its brightness varied on the time scales of a few days, which is also a very perplexing thing. And it meant that the total size of the quasar could not be more than a few light days across. Since it was so compact and so luminous, the only way it could keep from blowing itself up with its own radiation was if it was also very, very massive. Okay, so this was a conundrum. How could an object about the size of the solar system have a mass of about 1 million stars and outshine by 100 times a galaxy of 100 billion stars? And the answer came some years later by one of Martin Schmidt's previous graduate students. And that answer was the radiation from swirling material being sucked into a supermassive black hole. It was proposed in 1969. As you might guess, it was a controversial theory at back then, and now it's widely accepted. So that's quasar 3C273. So the next object is M106. M106 is a type 2 Seyfert galaxy, meaning that it has what's known as an active galactic nucleus. An active galactic nucleus is a very energetic nucleus, sort of akin to a quasar, but not nearly as energetic as a quasar. You can see in this image that there's quite a few galaxies that are also in view. If I stick my labeling program on it, you can see that there's quite a few, galaxies that are within this 3-degree field of view of M106. So as I mentioned, M106 has an active galactic nucleus, and it's also the host to water vapor megamasers. Okay, so what's a megamaser? A maser is the equivalent of a laser, which I think most of you are familiar with. But a maser operates at microwave wavelengths instead of visible or infrared light wavelengths or frequencies. A megamaser, so masers and lasers, we develop in laboratories. You have lasers and laser pointers. They're used for a whole host of industrial reasons, as are masers. And in these devices, one of the requirements for to achieve lasing or masing is that you need to have a very long path length. And in devices that you make in the laboratory, you make an optical cavity with mirrors such that the light bounces back and forth many times, such that there's a long path length. Okay, well, megamasers occur extragalactically, and they occur naturally. Okay, now obviously there's no mirrors, they're cavityless, but their large size provides naturally the large path length required for the conditions of masing. Now, also in a device that you make in the laboratory, to get it to maze, you need to achieve something called population inversion, meaning that the majority of the atoms inside the mazing material need to be in excited states, and you achieve this by optically or electrically pumping the laser in your laboratory device. Well, in megamasers, in these naturally occurring devices, they're not really devices, they're natural phenomenon, they're pumped by the emission of the active galactic nucleus itself, by the active galactic nucleus accretion disk. Okay, much like the quasar is bright because there's this material swirling around the black hole at the center of the quasar, this accretion disk of material that's revolving around and getting sucked into the center of this active galactic nucleus. It radiates energy, excites the atoms in the accretion disk, and the right conditions in some cases are met, and you get a megamaser. So why all this talk about megamasers? They're actually of scientific interest. The water masers in M106 enabled the first direct measurement of the distance to a galaxy for the first time. And it turns out that this is actually simple enough that I think I can explain it. This is data from the 1999 paper. What it shows here is the accretion disk revolving around the center of the active galactic nucleus in M106. We can look here at the scale. Once again, this is millimeter wave imaging, and we're not down in the microarc seconds, we're in the milliarc seconds. But once again, this distance here is 3 milliarc seconds. So this entire image is just a tiny fraction of 1 pixel in my image. So we're looking just at the tiny center of M106. And they actually have enough resolution that they can then resolve different megamasers in the accretion disk. So each one of these triangles here and here represent megamasers, as do these circles on the front. Okay, so these megamasers are in this disk that is revolving around, okay, such that the ones, oops, sorry about that. Uh-oh. Okay, we're back. Such that the megamasers on the right-hand side are revolving around, and they have a component that's moving towards us. And the megamasers on this side are moving away from us, okay? Meanwhile, all of them are receding, moving away from us based on expansion of the universe. You know, the whole M106 is moving away from us. So they can do, because of these megamasers have very, very narrow line widths, you can do very, very good spectroscopy on them and measure their Doppler velocities. And you can see here, the megamasers in the center have a slightly positive line of sight Doppler velocity. The megamasers that are on this side are moving towards us. I don't know if I had us revolving when I explained it, but these ones are moving toward, these ones are moving away from us faster, okay? And the ones on this side are actually moving towards us. You can see that the velocity is negative. So the speed due to the rotational velocity is greater than the speed due to the receding object due to the expansion of the universe. So based on this, the bottom line is they can figure out the velocity that these megamasers are rotating around. Furthermore, the megamasers on the front have a tangential velocity because they're moving across. So you can see over a 3-year time period here, you can see from 1994 to 1997, they can look at these various megamasers on the front, and their right ascension actually moves over the years, so that they can figure out not only the velocity of these megamasers, but also the angular velocity. Okay, so knowing both the velocity and the angular velocity, then it's a very, very simple and direct trigonometry problem that you can hand to your little brother who has a pad of paper and a pencil, and he can calculate exactly how far away this object M106 is to us. And that's why here, when I give the distance, unlike all the other objects, we know the distance quite accurately, 24.8 plus or minus 0.5 million light years to M106. Okay, so that's it for M106. So we move on 3 months later, we're now in August. We can see on our star chart that the Milky Way is bright in the sky, and we're going to look at 4 different objects, M13, the Veil Nebula, M16 and 17, and the Rho O cloud complex, including M4. And that is the first one we look at. I don't have a whole lot of interesting things to say about this image, except for the fact that it's gorgeous. And there's a whole lot of things going on. This field of view is quite large. It's actually 2 images stitched together. So we're looking at about a 3 by 4.5 degree field of view in this image. There is here a reflection nebula that is illuminated by the star 22 Scorpio, a visual binary in the namesake of this area of the sky, the visual binary Rho O. In the center is a great example of dark nebula that gives a very good kind of window on the star's 3-dimensional feel when you can see this dark cloud that blocks out the stars that are behind it. In the field of view is Antares, which is the probably a star that many of you are familiar with. It's the 15th brightest star in the sky. It's very red and orange and Scorpius. And there are 2 globular clusters in this image, NGC 6144, and more prominently M4, which is visible to the naked eye. Look up in the sky at Antares, and you can easily see M4 on a clear night. It was the first globular cluster in which individual stars were resolved. And on the next chart, we will talk more about globular clusters. So this is M13, the Great Globular Cluster in Hercules. It's, I believe, the biggest and most beautiful globular cluster in the sky. It is 25,000 light years away, about 1/10 of the distance across the Milky Way. It was discovered by Edmund Halley in 1714, observed and cataloged by Charles Messier in 1764, who loudly stated, "I am sure it does not contain any star." So he might have been a pretty smart guy, but he was wrong on that one. But it was because he just did not have the equipment that was required. Soon after he made this statement, William Herschel, with the luxury of a better telescope, resolved it into individual stars, revealing its true nature. But really, what are globular clusters? It turns out that they're really actually quite strange things. They are spherically, tightly gravitationally bound collection of hundreds of thousands of very old stars, far more numerous and far older than the less dense open clusters. So they're completely different objects than open clusters. The distance between stars near the globular cluster core is on the order of the diameter of the solar system. It's kind of larger than the diameter of the inner solar system, but I think smaller than the diameter out to like the Oort cloud. Globular clusters are distributed spherically, like the dark matter halo in a galaxy, in contrast to open clusters, which are distributed in the ordinary matter disk of the galaxy. And this to me is sort of like a clue, right? That the nature and the origin of these globular clusters is unusual. And in fact, the origin of globular clusters is really not well understood and is a matter of current and it will be well into the future scientific debate of exactly, how these things got there. While their appearance might lead one to guess that there would be the existence of a large black hole in the center, Certainly, you look at this and the image I get is like a whole bunch of stars like going down a drain. And in fact, that is not the case. Their kinetic energy, in fact, wins out over the gravitational energy, resulting in ejection of stars over time in a process termed globular cluster evaporation. So it's the same thing as in open clusters, where the open clusters don't live forever because the objects have close encounters with each other as they orbit around and get flung out. Well, it turns out that the same is true of these globular clusters. So in fact, they're not like attracting more and more stars and getting bigger and bigger. They are evaporating away. So in fact, they won't live forever, which begs the question then, if they're very, very old objects and they don't live forever, why are they still here? Well, it turns out that the typical time scale for globular cluster evaporation is on the order of 10 billion years, okay? And well, the universe is nominally about 10 billion years, a little bit older than that. And that's why they're still around. They're all here, but they're all slowly evaporating away. So this image was 240-second, 16 frames. These are this is a relatively bright object, so you can do pretty well even with shorter exposure times. And I think I was actually pretty happy with this particular image, in that even with my system, you can see that quite a bit of detail in M13. Okay, so on to the next object, something far less exotic, but quite strange to many people, and that is Barnard's star. We think, and even I said at the start of this presentation, that objects, stars up on the celestial sphere are fixed. Well, in actuality, no, stars aren't fixed. We've been talking about how stars and globular clusters revolve around each other and get tossed out. In fact, all stars are kind of moving around. Most of them just not very fast. Well, Barnard's star is an unusual one, and this is exemplified in these two photographs. The photograph on the left is from the Palomar Sky Survey. It was taken around 1955. It's a 40-minute by 40-minute image, so this is not it's less than the full view of my imaging system. This image on the left is the image I took on 18 August 2020. Okay, and if you look, the exposures are a bit different, but it really is the same image. You can see star, 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 and that's star, star, and star, star, star. And in particular, you can see right here, there's this little arrow of stars right here, and that's this arrow of stars in my image. And then if we go down, you can see that there's this star just to the right and above the left tick mark, and that's that star right there. And then there's this very bright star, one of the brightest in the entire image, Barnard's star in 1955, and it ain't there in August of 2020, and in fact has moved up to here. And you can spend a lot of time looking at all these other stars, and nothing else has appeared to move at all. So this happens because Barnard's star both has a large tangential velocity relative to our solar system, and it is also, importantly, the fourth nearest star to the sun. So there's a lot of stars out there that we can see in this image, and that kind of makes Barnard's star kind of special in itself, and that it's the fourth nearest star to the sun. Its proper motion was measured by E. Barnard in 1916. And its proper motion is about 10.3 arc seconds per year. And if you care to do the math, given that this is a 40-minute field of view, and this was in 1955, it works out about right that with this proper motion of 10.3 arc seconds, it would have moved about yay far in this image. So lastly, on Barnard's star, in November 2018, a exoplanet, which has really been in vogue. The discovery of exoplanets is in the news a lot these days. Well, a super Earth exoplanet was discovered orbiting Bernard's star and named Bernard Star B. So on to our next image. This is actually two images stitched together, giving a very big field of view, about over 6 degrees across in this direction. And it includes a whole set of beautiful H2 region nebula that are dominated by this H alpha red emission. The most prominent members of this image are M18, an open cluster, and then the Eagle Nebula, which this whole thing is often referred to as the Eagle Nebula, M16. M16 is actually this open cluster within the larger H2 region nebula IC 4703, and then the Omega Nebula M17, which is over here. This area of the sky is most well known for the famous image taken with the Hubble Space Telescope, the Pillars of Creation. And the Pillars of Creation is of the Eagle Nebula, which this little eagle shape, which you can see, I think, a little bit better in my blow up here, my image of the Eagle Nebula. Needless to say, the resolution achievable with the Hubble Space Telescope is far better than what one can do with an 8-inch ground-based telescope. And furthermore, on the Hubble Space Telescope, it's a multispectral image taken with multiple different cameras using different filters, where they then do a significant amount of post-processing to render that image so that it's particularly beautiful to the human eye. But you can see the basic features, this main feature here, and these two pillars here. So even with a one-shot color camera on an 8-inch ground telescope, you can get some semblance of a version of the Pillars of Creation. Just to quantify these things, this was taken with a wide field camera on the Hubble Space Telescope, which has a resolution of 0.04 arc seconds, which is about 100 times better than the resolution of my telescope system. You can compare that with the resolution of the human eye, which is about 10 times worse at 40 arc seconds. And then, earlier I showed you the synthetic aperture imaging in millimeter wave, where you get down to these incredibly small resolutions. Okay, I will talk a little bit more. I did this image using the oblong L-enhanced dual band filter to enhance the H alpha emission, and I'll show a little bit more on that on the image of the Veil Nebula, which is right here. So this is an image of the Cygnus loop, including the Veil Nebula. The Veil Nebula is a supernova remnant, so it's one of those other different types of nebula that is formed from the expanding cloud of gas from a supernova explosion. As such, the supernova explosion is a very energetic event, and these gases are excited to very high energy states. Thus, you get radiation across the spectrum from the Veil Nebula in the radio, infrared, visible, UV, X-ray, the whole ball game. And obviously, what I show here is just in the optical visible. The envelope of expanding cloud of this supernova remnant is expanding at 1.5 million kilometers per hour. And based on this expansion rate, which they can actually can figure out by imaging many years apart very accurately, and they can see the expansion of the gases in this image. They can extrapolate back and calculate that the supernova occurred about 8,000 years ago today. Now, the center of that expansion is somewhere in this area right here, and there's been some amount of work to look for the remnant of the supernova explosion, either a black hole or a neutron star. And to date, that supernova remnant has not been identified. Okay, so on this image, I once again use this opto-long dual band filter, and I went the wrong way, which is here. So this is a diagram of the filter function, and you can see the filter is specifically to pick out the red H alpha line and the blue H beta line and green O3 line. I guess I'm doing a little advertisement here for folks that image stuff at TDS. If you're imaging nebula, this is a fantastic filter because the light pollution at TDS is really pretty. Yeah, it seems like it's getting worse and worse and worse every week. But this filter is just fantastic for imaging nebula out at TDS. Okay, I only have a couple of images left to go. You go out in 3 months later, it's November, it's very, very cold out at 10 p.m. The Milky Way has rotated away, and you look up in the sky, and this is the best time of year to image the Andromeda Galaxy. The Andromeda Galaxy, as I mentioned earlier, is the closest large galaxy to us. My system at 3-degree field of view is perfectly suited for imaging the Andromeda Galaxy. The Andromeda Galaxy is about the same diameter as the Milky Way, 220,000 light years across, and it contains about 1 trillion stars in the Milky Way galaxy. And the fact that this is a wide field and has so many stars in it made it useful just recently for experiment, well, not an experiment, an observation to search for dark matter. Dark matter, we know it's out there, but we don't understand what it is. Primordial black holes have long been suggested as a viable candidate for what this mysterious dark matter is. So primordial black holes are unlike like the black hole at the center of quasar 3C273 or the black hole at the center of M87. Those are massive black holes. They're huge. Primordial black holes are much smaller, are much smaller object, and they formed during the first 1 second of the universe, which was the only time that conditions were proper that such small black holes could have formed. Okay, at that time, during the first second of the universe was much denser, extremely dense, and also somewhat heterogeneous. Okay, not yet smooth. And in those conditions, these primordial black holes have been proposed. Okay, now we've never actually truly identified one, so we don't know if they exist, but they are, in that sense, hypothetical objects. Okay, and also good candidates for dark matter. So recently, in a 7-hour-long observation of M31 with the Subaru telescope on the top of Mauna Kea in Hawaii, it was used to search for microlensing events of stars in M31, the Andromeda Galaxy, by possible candidate primordial black holes lying in the dark matter halo regions of the Milky Way and M31. Okay, so I think that that you know from Einstein's theory of general relativity, that if you have a very, very massive object, it warps space so that light then no longer travels in a straight line. And in fact, a famous experiment was done during an eclipse looking at Mars, where based on the gravitation of Earth, that space was warped right near the path that went right close to the sun, making Mars appear as if it was not in the position that it should be. Okay, so by the same effect, if you have a black hole which is very massive, the light that goes past that black hole curves. Okay, and thus that black hole can act as a lens. Okay, distorting or magnifying the stars that are more distant than the black hole object. So when we look at this image of Andromeda, we're looking through the dark matter halo of our galaxy, and then we're looking at through the dark matter halo of the Andromeda galaxy at all these stars in the Andromeda galaxy. And if there are these primordial black holes in this dark matter halo, you would expect that microlensing events would happen, where the image of the Andromeda galaxy, the position of the stars, would be distorted by these intervening primordial black holes. Furthermore, because of the motion of the Earth, the position of these intervening primordial black holes relative to the stars in this distant object change. So if you take an image over a long time period, you should see changes in the position of stars. Okay, so this is the experiment that they did just recently, 2019, with the Subaru telescope. What's interesting to me is that, well, there's quite a few things that are interesting, is that the field of view of the Subaru telescope, using its suprime cam, which is positioned at the prime focus, the field of view of this system is quite similar to the field of view of my little 8-inch Celestron telescope. The resolution of the Subaru hyperfine telescope is 0.67 arc seconds, limited by scene conditions, which is about 4 or 5 times better than the resolution of a little ground-based Celestron. But doing, they have a much better camera, much bigger camera. It's made up of 116 sensor chips, where the chips are really not so different than the sensor chips that are in my system, but it provides an 870 megapixel camera, so they can connect a lot of data fast, and they can collect a lot of light with their 8-meter mirror. So they did this experiment, and they were expecting that if there was a primordial black holes that could account for dark matter, that they would see lots of these lensing events. But in fact, they only saw one single, after churning through all the data, they only saw one lone candidate primordial black hole lensing event in the experiment. And it's shown here, where this is the reference image. This was the target image taken sometime later. The difference then showed, what looks like something, and then they do image processing, where they say, if we understand that there's a primordial black hole in the middle, it should then cancel out this image, and this shows the sort of uniform field based on a hypothetical intervening primordial black hole. But the bottom line is that they did not detect nearly as many of these events as they were expecting, and that result put a stringent upper bound on the abundance of primordial black holes in this mass range to explain the presence of dark matter in the universe. A couple other things of interest, so that you have a better feel for the meaning of this experiment. The solar mass range that they were looking at was between 10 to the minus 11 and 10 to the minus 6. So 10 to the minus 6 is about, solar masses is about the mass of the Earth. 10 to the minus 11 is way, way smaller than the mass of the moon. So that's the size of these primordial black holes that they were looking at. There remains a range of primordial black holes that are still need to be investigated between 10 to the minus 11 and 10 to the minus 14 that was not covered by this experiment. But all the other possible primordial black holes outside the range I just mentioned, from minus 14 to minus 6, have already been ruled out as candidates for the dark matter that we calculate exists in the universe. And then the other way of characterizing, another way of characterizing black holes is this event horizon radius, the Schwarzschild radius. And these primordial black holes that we're talking about in this region are really small, right? They have event horizon radiuses of like between 3 millimeters and 3 nanometers. So you pack a lot of mass into a very, very small thing if you're a black hole. And my final image is far less exotic and closer to home. A comet, only 0.7 astronomical units away. Comet NEOISE was discovered on March 27th by 2020, just last year, by the Wide Field Infrared Survey, WISE, a NASA infrared wavelength telescope, as part of the Near Earth Object WISE program. So they're searching for near Earth objects and found one. It is the brightest comet in the Northern Hemisphere since Comet Hale-Bopp in 1997. For your enjoyment, this is a photo from TDS on the same night I took that image with the telescope of Comet NEOISE. This is a case, I think, where taking a photograph with a regular camera with a 40 millimeter lens is a better deal than a telescope. So just a few notes on comets. They're made primarily of ice, in contrast to asteroids, which are made primarily of rock. The comet has a nucleus, which is about 5 kilometers in diameter, so it's a little thing. As the ice outgasses, it's warmed, and it's warmed by the sun, and it forms a visible atmospheric coma. The comet tail is caused by the solar wind and therefore points in the opposite direction of the sun, not opposite the direction of the comet's motion. And in this image, that's clearly seen, where the tail is pointing opposite the direction of what you see the remnants of sunset here at TDS. And for those of you that are have spent too much time at TDS, yes, I did Photoshop out the power lines in this image. So that concludes my presentation. I think that in this group, most of you enjoy astrophotography, otherwise you wouldn't be in this group. But for the intended audience, I was going to ask that, the question if astrophotography is right for you. Astrophotography definitely is not right for most people, but if you enjoy spending a lot of cold nights under the stars, fiddling with cameras and computer programs, trying to get systems to work without getting upset when they don't, and learning about astronomy, then maybe astrophotography would be a good endeavor for you. So that concludes my talk, and I'm happy to entertain any comments or questions that you might have.
Say, Bill.
Yeah.
Excellent presentation. Got a question on Pleiades and some of those other photos you took. Do you put some special star filter on to get those star effects?
Right. Yeah, let me go back to the Pleiades. Am I still sharing? So yeah, I do put, so in the setup that you have for using the Hyperstar, you have the cords that connect to the camera, and there's no way to get rid of that, right? So what I do is I made a little jig that is the remaining 3 arms of a cross that I stick on the front, so I have the dew shield, right, that's attached, and the cables then are tied to the dew shield, and I have just a little jig that I made that has the other 3 arms of a cross. So you're just seeing the pattern, the diffraction pattern caused by essentially a full cross in front of just like you would in a new telescope. Does that make sense?
Yeah, thanks.
Yeah, they sell. I mean, I think they sell various different things for doing just what I did, just by homemade. And you can also get a little jig for your cables that make the cables go in kind of an arc away from the camera that will eliminate any star diffraction pattern that you get from having those cables there, because it kind of gets smeared out. If you just have the cables and you don't do the other 3, make up a jig for the other 3, then you get a rather, in my mind, unaesthetic, ugly, unsymmetric pattern. And I'm sure some of the images I showed here are old enough that I didn't have the cross jig on that had that, but I'd have to go through them to find the example of the bad ones.
Good, thanks.
Hey, Bill, you might explain to somebody that the group the differences between a Hyperstar setup and a standard setup, because that's using Hyperstar is pretty specific to celestrons as opposed to standard imaging off of a cassogram. You might want to explain that.
Right. Yeah. So I did have that one chart where I just showed that this one. I showed that the standard setup focusing at, I guess I should swap. Focusing at the secondary as is normally done at f10 and 2000 millimeter, and focusing here. Are you suggesting I do more than that, or? I mean, yeah, and it is.
You're imaging at f2. You're at
yeah.
Hyperstar. You're imaging at f2, correct?
Right. Yeah, exactly. 400 meter focal length f2. Right, and 3-degree field of view. So I guess I should try and make that more clear. But yeah, I understand. Thank you. I don't know. Can you? I mean, I assume you can get the fittings to put a Hyperstar on like a Meade Cassia grain. I don't know.
Actually, you can't.
You can't?
No, you cannot. I've had a Meade for almost 20 years, and I'll guarantee you there's no way to put Hyperstar on it.
Interesting.
Or FastStar. The setup of the secondary is completely different than what Celestron has done.
I see. So it's totally specific to Celestron.
Yes, it is.
Okay, got it. I was not aware of that. Or maybe I was aware of it and forgot. That happens a lot these days. So you know what? I guess I could show the coma correction. In case anybody's interested. Yeah, so the object labeling, this is something that's not, if you want to do this homebrew, it's not hard to do. I just use the online database from NASA. So there's a website for that has a database of extragalactic objects, and you just need to learn how to use it to download a list of objects, in the field of view that you're interested in. And then you can I also just use a table of M, N, G, C, and IC objects. and that's the input. And then you need to identify 2 or more known objects in your image field so that you can correlate 2 or more pixel positions with right ascension and declination. And the code's quite simple, right? It does the conversion from the celestial spherical coordinates to the image Cartesian coordinates. It does a best fit for camera rotation angle and pixel pitch, and then uses the Python pillow package for doing the text and drawing insertion, and also JPEG image IO. So that code is pretty simple to do. And then the image. So then this is when the data is taken from the table, it also gives the size of objects. So you can see this one is labeled with circles that show the nominal size of the objects that I identified. And these are not extragalactic, right? These are inside the galaxy from that database. The coma correction that I do on a lot of the images, just depending on how much energy I have, is based on Richard Lucy deconvolution using locally calculated point spread functions. And you implement it on just star fields only because it'll just make a mess of extended objects. And the references are given here, the original Lucy paper on doing the deconvolution iterative technique for image restoration. And I had the idea of doing it locally, but I'm sure many other people did. And so I did dig up an actual paper that describes it, 2008, and you can find this paper. And doing the code. So here's from that corner. It's this corner of the image that I'm showing up there. This is without coma correction. And you can see the bad coma, all these stars turned into triangles. And in the coma corrected, it's much better. The code basically, it partitions the image, calculates point spread function in each partition. I only use the corner and edge partitions to actually process. And then you execute the Richard Lucy deconvolution using each one of those point spread functions. And it's much easier than you think, and that most of this has already been done for you using various packages that are available in Python. The AstroPI package for the fit image IO, the photo utils part of the AstroPI package had background estimation and star detection and extraction for forming the point spread functions, and the SkyKit image package for the Richardson-Lucy deconvolution. So you don't need to learn these things from the bottom. And I'm sure, I guess, a lot of the more sophisticated packages that folks use for doing astrophotography might have this kind of thing built in. But I had fun doing it this way. So.
I got another question, Bill.
Sure.
You mentioned 2 software packages that you use in post-processing, nebulosity and raw therapy.
Yeah.
I guess I basically use a setup like what you have in the background there, just with a Sony camera on a tripod for the star tracker right now, process raw images. But what does the raw therapy do for you?
Okay, so raw therapy, if you're familiar with the more commonly known Adobe software packages, Photoshop is a photo editing program, and there's a freeware version called GIMP, which is kind of the equivalent to Photoshop. Adobe has kind of a sister program to Photoshop called Lightroom, and raw therapy is the freeware equivalent to Lightroom. Raw therapy is a very sophisticated and mature product. I have not encountered any bugs, and it does lots and lots of stuff. But the difference is that a program like Photoshop is for photo editing if you want to go in and change some specific area of your image. Lightroom and raw therapy, they have functions that act on the whole image. Okay, you don't edit different parts. You just run algorithms that operate across the image, and it provides every conceivable type of operation that I know of to do, including things like fine-tuning the exposure. I mentioned this nonlinear pixel stretch. So, you have a whole host of different ways that you can adjust the nonlinear exposure level. You can do plaque level correction, contrast, local contrast, color balance, color saturation, linear filters, vignetting filters. The local contrast is a huge one that you should definitely look into, that I'm sure is included in the advanced things, PixInsight and all those kind of things. I'm sure have and Maxim and the likes have that built in. But they're rather sophisticated tools in doing local contrast in many different ways, and the color balance in different ways, and noise reduction in different ways. And like I said, it is not an astrophotography program. It is just a digital image program. So, professional photographers use Lightroom just to process their images straight off of their cameras. I think that most professional photographers don't store their images as JPEG already processed. They store them in RAW format, and then apply all that processing that is typically done. People that store their images as JPEG, well, it's being done on your camera for you based on the particular settings that you choose on your camera. If you store the raw data, then Lightroom or raw therapy lets you do that yourself in just the way you want to do it. Okay, so I think that this is actually a very good example. If you go from number 5 here to number 6, right? This is obviously a much more appealing image here than this one, and that's just from fine-tuning all these basic things that are operating on the full image. Does that answer the question?
Yeah. Does that take, what's the input format? Is it like a TIFF that you provide to it?
Exactly.
Okay.
Yes, that's exactly what I do. I do up until image 5, it's all done in nebulosity as a FIT and FIT, and then nebulosity allows you to output as a 16-bit TIFF, and that TIFF is what you want to use as the input to raw therapy. Now, raw therapy does, since it is very mature, it does accept a wide variety of raw input formats. So, for instance, my Olympus camera, right? Olympus has their own proprietary raw format, and raw therapy natively reads the Olympus format, as it does Nikon's proprietary format, and I'm sure it does Sony's raw format as well, because it's used by so many people.
Great, thank you.
And it's free. And it's available for Windows. I assume it's available for Mac. I don't know.
Anybody else got questions? Oh, great. Thanks, Bill. That was a great presentation.
Okay, I'm glad that you enjoyed it, and I can see that there's still quite a few people that are here, which means that it wasn't too bad. So that said, I wanted to ask one question of you. What did you think of this presentation for its intended purpose, i.e., for kind of a junior college level astronomy And do you think I should continue to pursue avenues through San Diego Astronomy Association for outreach as an educational thing for, oh, and I see now I'm looking at their comments. So there's probably more questions here in the chat. I was focused on the presentation, not looking at the chat screen, but I'll hopefully there's, well, let me see if there's any data files can be. Yeah, Martin Schmidt and the Smithsonian. How about that?
So Ken, you've been working with the outreach program for quite a while. You got answers for Bill?
I don't know if any of you are involved in outreach through SDAA, but you know, that was kind of the object. You know, I was hoping that I could maybe, you know, identify other junior colleges, but then again, maybe you heard this talk and you think that it's not appropriate, which would be plenty fine to know. I'm not, you know, I'm not proud. So if you think it's not good, let me know.
Hey, Ken, what do you think, buddy? Unmute, buddy. Hit that unmute button.
I thought I unmuted myself. I'm better off muted anyway. Yeah, the problem is venues and getting people to come. Like, you know, if you can go to a junior college, this would be great. Library would be hard because the public, yeah, they want to see pretty pictures. They don't want to know how they've done.
Right.
And I tried to do something with, upon request by Sycamore Canyon Gooden Ranch. And I was thinking, let's just do wide field DSLR on a tripod, you know, because that's easier and everybody can do it. It was advertised, nobody signed up. Right. So, you know, it's a hard nut to crack. But right. I think the junior college level would probably work out pretty well for this level of presentation.
Right. Well, that's what it was aimed at. Yeah. So if anybody, you know, if anybody ever runs across like, oh, you're a junior college astronomy teacher in San Diego, you know, let me know. And I think that actually, you know, it's the Zoom thing that, you know, even when COVID's over, there might be a class that would entertain the idea of me just doing it via Zoom into their class, right? And of course, I could always show up for their class too and do it that way. But
you can always send an email to Mark Lane. He's the astronomy prof. He and Scott Cardell at Palomar College. Okay,
that would be great. Well, you know what? I think that my if you can send me that contact information, that would be great. Or just their names. You can send me their names.
I'll put them on the in the chat.
Okay, that'd be great. Thank you.
Mark Lane and Scott.
There, and then on the side, if you know them, you can tell them that if whether or not they should say yes or no.
Yeah, I know. We all know these guys real well.
Thank you, Mark Lane.
And Scott Cardell.
Scott Cardell. Yeah, I kind of have a captive audience, you know, since my buddy is the instructor at La Positas. But finding other ones is a trick.
I'll give you a little anecdote. I have a friend who got her PhD in astronomy at University of Arizona. I went out to visit her and we did some stuff out there. And she said, well, they got the great Adam Block to give a talk to astronomy students at the University of Arizona. If you or I or anybody on this, in the AISIG group, was listening to Adam Block, would take voluminous notes, right? Because we wanted every little bit of information he has. The college students basically didn't take notes and didn't really care because they just wanted to get an impression because they weren't actually going to do it.
Right.
So that's a little data point to keep in mind with college audiences.
Right. Right.
But your overall talk with elements of imaging and the astrophysics might just hold them.
There you go. Well, thank you.
Sure. Good luck.
Well done. Thank you.
Thank you, George. I appreciate it.
Enjoyed that.
Oh, someone asked, what is TDS? Okay, well, that's Tierra del Sol. It's the San Diego astronomy site just east of San Diego. Oh, and someone answered. It's me catching up.
And I was afraid to put a dollar value on her question. But my rig probably cost 10,000. So does yours.
I have a chart on that. I have a chart on that.
Oh yeah, show the chart. That sounds great.
The true definition of astrophotography is a hole in the sky you blow money into.
Yeah.
The ultimate black hole.
There it is. So that's the cost of the system.
Don't see it yet.
Yeah, you're not sure.
I'm not in share. Hold on. Oh. Share screen. Okay, it's coming up in 1 second.
Oh, okay.
There you go. So that's the cost of the system. The Celestron and these are sort of current prices, I think, kind of current prices. But you know, I bought my. So you might ask, why am I using the wedge and that setup? It's because I bought the telescope from when I retired. I mentioned to a friend at work that I was, you know, gonna buy a system and start doing imaging, and he said, "Hey, I have a Celestron 8, and I never use it, and it's like pristine." And I knew the guy, and he was totally meticulous guy. And I said, so I bought it from him for cheap, and it was what it was, right? So that's why I don't have a proper EQ mount. And you know, I put the system together to be it's my first and still my only imaging system, and it was meant to be forgiving, so that I could get you know, results that were fun without too much heartache, and to be relatively low cost. And then, you know, I figured I'd play with this system, and then if I wanted to, you know, get something more sophisticated, expensive, or whatever, I could move on. And so we're now 5 years out, you know, of playing with this system, and I'm still having fun with it. So there you go. I mean, and it really is, and this really is most, assuming you have a laptop that's capable enough, but even then that would only be another $1,000 these days for the laptop. So that's basically, you know, there's always a few odds and ends, but these are all the main items. So $6,000.
I've got another question. Of course, the right way to do this is with an equatorial mount, but if you have altitude azimuth mount, like I've got a Celestron 6SE, so it's going to rotate a little bit. Can you make your imaging software take into account the rotation and line these things up properly anyway?
Well, I mean, the basic answer is you need a wedge, right? You need to take your alt-az mount and turn it into an equatorial mount. If you don't, right, then, you know, your images will rotate. And, you know, you can say, well, I'll take, you know, so that, you know, they'll rotate, the frame rotates.
Yes.
Right. So, you know, that's unavoidable, right? The frame will rotate. So then the question is, well, you know, I could take lots and lots and lots and lots of, say, 10-second or 20-second exposures, and then have the software, you know, rotate them as they go, and then you'd only have 10 seconds of rotation. But you know, you don't want to go there. You just don't want to try and do it that way. You'd be way better off getting the $700 wedge, and given it's heavy and in some sense non-aesthetic, but it solves the problem.
Thank you.
I don't know, maybe with your, maybe, you know, maybe with your particular alt-az mount, then the wedge doesn't work. I don't know if that, I don't know exactly what you have, but you really don't, if you want to do imaging one way or another, you should have an equatorial mount.
No, I could easily get a wedge and install it.
Right.
Any other comments and questions? All right, folks. I put up the link in the chat box for the data for next month's meeting. If you have any questions at all about getting to that data or being able to download it, please send me an email, either taro@sdaa.org or president@sdaa.org. And I'll put this up on the group's IO page as well. So anybody that didn't make the meeting tonight can give that a trick. All right. Anything else? We'll let everybody go. Appreciate it.
Very good. Thank you all.
All right. You guys have a great evening.
Okay.
Care.